Hello, everybody. I just wanted to do a bit of a check-in. We're about halfway through the semester with our material here, and it's been a tough time, a challenging time for a lot of people with a lot of different responsibilities going on. Uh, and I just wanted to make sure that once you get the chance, when you get the chance, make sure to take some time for yourself and make sure that you're in the best spot possible so that we can get through the rest of the semester in as positive and healthy way as we can. Okay. We have one topic that we wanted to talk about in this lecture, and that is Newton polynomials. There's actually another way of constructing polynomials that pass through different points, and it's going to be a completely different method than we talked about with Lagrange. So we're going to focus on that for today, and here we go. So basically, Newton polynomials is an approach to finding an interpolating polynomial, an interpolant, that abandons the idea of basis functions and instead builds a polynomial in a different sort of way. So the goal is no different than it was. And really, this is only providing us with another option to building a polynomial that you might find to be more attractive in certain situations, that might be more useful in certain situations. But really, it's just going to give you something that's mathematically equivalent to what you would get with Lagrange. But it's kind of a cool method, and it results from some really, I don't know, interesting, fun calculations. So we're going to represent a polynomial in a bit of an alternative form here. The Newton form of an interpolating polynomial is one that does this. So suppose you're given a bunch of points, x1, x2, x3, and so on. Okay, p of x, our Newton polynomial, is going to do this. Constant plus another constant times x minus the first point, plus another constant times x minus the first point, x minus the second point. And then it goes all the way through, and then the last term is going to have a whole bunch of x minus a bunch of different points multiplied together in a product. But notice that we don't get powers of x minus a particular x value. We get x minus a particular x value, and then x minus an x value, and x minus another x value, and so on. So it's a little bit of an interesting way of setting this up. You're going to get a polynomial of degree n minus 1 at the end of the day. You can count that for yourself. If you have x minus the first point, x minus the second point, all the way through to x minus n minus first point, there are n minus 1 x's there to be multiplied together in that biggest term. So we get a polynomial of degree n minus 1, which is the very same that we would get as Lagrange interpolant, right? And a Lagrange interpolant would be of degree n minus 1 for a set of n points as well. Okay, this form holds some interesting advantages, but it might just look really complicated at first glance. It might not be very obvious why this is, but it'll become clear when we play with this form a little bit, okay? So let's use what's at the top, and let's try to plug in one of our points. So if we try x1, y1. So plugging in x1, which should give y1, given a point x1, y1 that we want to be on this curve. Well, look what happens. If we are to plug it into this equation up at the top of the page, this right up here, if I put x equal to x1 in here, I get x1 minus x1. I get x1 minus x1, x1 minus x2, but it's not going to matter because the x1 minus x1 is going to kill it, and so on and so forth through all the different terms. So you see, we're going to get a1 plus a2 x1 minus x1 plus a3 x1 minus x1 x1 minus x2, and we have to add all of these different terms until we get to the very last one, but we can see that we're every single one of them is going to die because we always have this x1 minus x1 in each one of them. So as we can see, right, this term here, that's 0. This one here, that's 0 because of the x1 minus x1. This one down here, also 0. So that tells us that that p of x1 equals y1 is going to equal just a1. So that means that, okay, if we have a polynomial in this term, that first constant, this first constant right here must be the first y value, the y value associated with x1 that's right there. Okay, well, we're going to keep building on that. Similarly, we can see if we plug in the second value. So we're going to plug in x equals x2 now. So I'm going to write the same sort of thing here, plugging in x equals x2, which should give y2. What will we get this time? Well, it's going to be the same sort of thing. This is going to be a1 plus a2, x2 minus x1 this time, plus, and then the next one's going to be a3, x2 minus x1, x2 minus x2. Hey, this one's going to be 0 now. And then we're going to go all the way through those different terms, and the last one's going to have x2 minus x1, x2 minus x2, all the way through x2 minus xn. But you can see, right, this one here is going to be 0, this one here is going to be 0, the corresponding products are going to be 0, but we have one more term that survives this time. This term right here is going to remain non-zero. So essentially, this is gone, this is gone. I know that a1 is y1 from before, and I can solve for a2. a2 is just going to be the subtraction of y2 minus this a1, which is y1, and I can divide by the x2 minus x1. So I would get y2 minus y1 over x2 minus x1 equals a2. Okay, you might ask yourself for a second, well, what if x2 is equal to x1? But if x2 is equal to x1, that means they're on the same x value, and if they have two different y values, no polynomial can go through two different y values at a single x value. So that's not something that we have to worry about. Okay, so interesting. We have that a1 is y1, but a2 is kind of this difference of y2s and y1s over x2 minus x1s. It looks like kind of like a slope, actually. But there's more. You can show that this kind of these differences, this difference of y2 minus y1, x2 minus x1, it's those kinds of quantities that are going to pile up inside a next difference for a3, and they kind of become this nested, divided difference scheme. So a3, it turns out, it's a lot of work. You can show it, but it would take, you know, a few more lines and a lot of ugliness. You can get that a3 is going to equal y3 minus y2 over x3 minus x2 minus y2 minus y1 over x2 minus x1 over x3 minus x1. A pattern begins to emerge. And we're going to set up a scheme that's going to allow us to calculate for each of those different a coefficients that give us that polynomial at the top that we started with. So here's how we're going to encode it. There are lots of different notations out there, and I want you to use whatever you're comfortable with. I like what I've used here. I think it's nice, and I think it makes some sense to my crazy brain. But let me walk you through it a little bit. So we're going to start with, maybe I'll write this as a first step. We'll start with points xi, yi for I equals 1 through to n. And then once we've got that, you can define the first divided difference with respect to xi and xi plus 1. So these are consecutive y's over consecutive x's. We define this as f. I used square brackets there because it's not really a function. It's more like a weird notation sort of thing. So xi plus 1, and it's going to be the difference of consecutive y's over the difference in consecutive x's. This here defines a difference in itself that in the next step, right, the next nested layer up is going to be inside the numerator. So see, I've taken each one of these things and put them in the numerator, and they appear consecutively in a certain sense, right? You can see in the formula for A3 at the top, y3 minus y2 over x3 minus x2, and then y2 minus y1 over x2 minus x1. And you can see here that with this f of xi plus 1, xi plus 2, and xi plus 1, you have that sort of consecutive difference, but not between y values, but between the first divided differences that we talked about, the first DDs, if you will. And similarly, you can extrapolate this up, because then you would take the ratio of these things to get the next layer, and so on. Notice that at each step, the denominator gets further and further separated. So the second divided difference has the difference of 2 here, xi plus 2 minus xi. As we can see in this formula for A3, it's not x2 minus x1, it's not x3 minus x2, it's x3 minus x1 at the bottom. How do you remember that? It's going to seem super, super complicated, and yet all of this is going to tumble down into this beautiful table that is going to be really easy and kind of fun to use. Okay, at the end of the day, coefficient AK in the Newton polynomial, so A1, A2, A3, and so on, those are always equal to the k minus first divided difference that starts with a x1 here inside, so fx1 xk. So essentially, we have to end up finding the first, the second, the third divided differences that have an x1 at the start here in order to get those coefficients. Again, I know it sounds really, really weird and complicated and ugly, and you're like, why are we doing math right now? This is terrible. Just hang on for like 2 more minutes and you'll see some beauty. So this might seem really extraordinarily complicated at a glance. I'll tell you, it's something else to explain here in front of a camera to nobody. But the beauty of this method is, starting with A1, each subsequent coefficient can be easily computed using the previous ones. So I'm going to illustrate this for the second degree polynomial case. And then we're going to kind of extend it to a third degree. And then we're going to do an example so you can see it for yourself. So here's how we set up a table like this. Here are the x values. Here are the y values. So I just write them here, here, and here. X values here, 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 y values. Okay. As we talked about before, this first y value is going to be your very first a value, the first coefficient in that polynomial. And then you can construct your divided differences by taking differences in y over differences in x. That's the first divided difference, and that's what this is. This is what we called f of x1, x2. This is what we called f of x2, x3. And you can see I use exactly these values. y2 minus y1 over x2 minus x1. y2 or y3 minus y2 over x3 minus x2. Then on the next step, to find the second divided differences, I'm going to be taking the differences in these quantities that we get, in this f that's in this slot on the table, in this f that's in this slot in the table. We're going to take the difference in those over the difference in, if you go all the way back down the tree, the difference in x1 and x3. So see, you see f of x2, x3 minus f of x1, x2 over x3 minus x1. So that's kind of how this is going to come together. And we're going to do the same thing for 4 just to get this down so we feel comfortable doing an example. So same sort of deal. We're going to, so one more thing above. Once we've got these, it's this term right here with the f of x1, x2. That's going to give us our A2. And it's this one with the f of x1, x3. That's going to be our third coefficient. And once we've got those coefficients, we've got the polynomial. And we're done. Remember that all of these things are just numbers. You're going to see that in the last example we do. But as I said, we're going to create our own one, but for a third degree polynomial case, so using 4 points. So suppose we have 4 points, x and y. So x1, y1. I'm going to give myself some room here, actually, because it's going to be big. x1, y1, x2, y2, x3, y3, and x4, y4. So to do this, we need our first divided differences, and this is going to be f of x1, x2, and this is nothing more than the difference in y's over the difference in x's. There are going to be 3 of them this time. The second one's f of x2, x3. This is the difference in y's over the difference in x's. And the next one down is the same thing but with 3 and 4. And this is going to be the difference in y's over the difference in x's. You might think to yourself, okay, wait, if all you need are the ones on the top, right? Like if I know that I'm just looking for the coefficients of this polynomial, and this one here is my a1, and this one here is going to be my a2, like why am I bothering to calculate all the ones down below? But the thing is, I need this calculation right here to calculate the next coefficient up. I need everything in this tree ultimately to get all of the different polynomial, or all the different coefficients to the polynomial. So the second divided differences, let's just relate these through those kind of trees like this and this, this and this, this and this. And similarly, on the next step, we're going to have f of x1, x3, and this is going to equal not y3 minus y1. It's the previous f's, right? So f x2, x3 minus f x1, x2. And this goes over x3 minus x1, like that. And down here, this is f of x2, x4. And this is equal to f of x3, x4 minus f of x2, x3 all over x4 minus x2. And see, we have to go one more layer deep to get that last coefficient. The third coefficient is given by this ratio right here. I guess it's big. This is it right here. This is going to be our A3 in our polynomial that we described at the top. We have one more to find, and that's our third divided difference. So third d, and that is going to be, and hopefully you're starting to see that pattern more naturally now, f of x1, x4, and that is equal to f of x1, f of x2, x4 minus f of x1, x3 all over x4 minus x1. So only one of those, that's the last one that we need, and this one here is going to give us the coefficient A4. Crazy. Let's apply this to an example, because all this really is kind of a formulaic approach for how we would calculate those coefficients. It's nice to actually be able to do them. Okay, so we're going to find an interpolant in Newton form that passes through the points 1, 0, 2, 2, 4, minus 2, and 7, minus 1. So we need, let's actually write down the Newton polynomial to start with. We are looking for the Newton polynomial, and it's going to look like this. P of x equals, there's a1, we have a2, x minus the first x value, x minus 1, plus a3, x minus the first, x minus the second, there's the second x value right there. And then the last is going to be a4, x minus the first, x minus the second, x minus the third. Okay, notice that it's really interesting, right? That the fourth is never really involved, and it's kind of an arbitrary choice for which ones that that you decide to use here, but it turns out that that's all that we really need. If you were to include another term, you'd have too much, right? Another term would make this a 4th degree polynomial that would then be too high order to be able to fit in general to 4 points. So uniquely in any case. So all we need are these terms right here. It is kind of arbitrary what you choose, so I tend to just put them in order from least to greatest. And the coefficients for these, the different a coefficients, can be determined by using this scheme. The different coefficients can be determined using the divided difference scheme. So let's do it. Let's do it. Actual example here, and you'll see how snappy this is. X and Y. So the different X and Y values here are going to be, what should I use here? Let's use green. Let's use green and red. So let's see. X would be 1, 2, 4, and 7 here. The corresponding Y values would be 0, 2, -2, and -1. Okay, we already know from before where we're going to be able to find those coefficients. So that is going to be something that I kind of outline at the end of the day. But let's start to construct our divided differences here. So first, DDs. The first DDs, there should be 3 of them. Maybe I'll give myself a little bit more room here. 2, 4, 7, 2, -2, -1. 2, 4, 7, and then 2, -2, -1. Okay, our first divided differences. Difference in y's. Maybe I'll write this out. F of x1, x2 equals 2 minus 0 over 2 minus 1. That's going to be 2 over 1, which is 2. Cool. F of x2, x3. That's going to be the difference in y's over difference in x's, so -2 over 4 minus 2. And I think this turns out to be -4 over 2, which is -2. Doing a quick double check of my notes there. Because I am doing this all like on the fly, but I did do this ahead of time to make sure that I didn't, so I have something to check back on. X3, x4, I'm going to take the difference of -1 minus -2 and put that over 7 minus 4. And that's going to be -1 plus 2 is 1 over 3, so 1/3. All right. So we've got our first divided differences, our second divided differences are going to take these values now. -2, -2 over, and then the corresponding x values, this one and that one. I should entitle this, and that'll make it more obvious. So this is going to be f of x1, x3, and this is going to be, yes, -2 over 3 minus 1, and that's going to be -4 over 2, which is -4 over, it was 4 minus 1, that's why. 4 minus 1, 4 and 1. There we go. I think we're good now. -4 over 3, which is -4 thirds. That's what should go there. And then we need f of x2, x4, and that's going to be here 1/3 minus -2 over, and then this time x2, x4, it's this one and this one. So 7 minus 2. Oops. And if you work this out, 1/3 plus 6 is, or plus 6/3 rather, that's what 2 is 7/3, and I'm dividing that by 5, so I think that's 7 over 15. And we have one more to go. Our third divided difference is going to be given by f of x1, x4, and we're going to take the difference in those last values that we calculated, so 7/15 minus the negative 4/3, and I'm going to put that over 7 minus 1. And if you work this out, I think you get, I get 3/10 in the end, just manipulating some fractions and good stuff like that. Okay, so at the end of the day, we want those coefficients. You can see there's the structure like before. Each step depends only on the ones before it. And this here, that's our A1. This here, that's our A2. This here is A3, and it looks like this here is our A4. So we can get our Newton polynomial. So the Newton polynomial would be, and if I wrote it down, we get P of x equals 0, that's our first A1, and then plus 2 times x minus 1 plus, we need a minus for the next one, so minus 4/3, minus 4/3, x minus 1, x minus 2, and then finally plus 3/10, x minus 1, x minus 2, and x minus 4. And you could verify then that every single one of those points do appear on that polynomial. This is the polynomial that goes through every one of those points. The Lagrange and Newton polynomials look really, really different, but they're mathematically the same because they've got to be. And that's a really important thing to note. So I think that's where we're going to leave this for now, because the next step here is going to be to do some coding. So, again, we are in the middle of the semester. It's been a rough patch for a lot, I know, and so I just wanted to make sure that everybody's doing okay. I wanted to say that we will be revisiting this topic in the next video to talk a little bit about how to code it, because it's a bit crazy, but I'm kind of excited for how I managed to figure it out, and I'm hoping to share that too. But given that lesson, and given the words that I had at the start, and this whole, you know, people being stressed and you know, being under some pressure and so on, I just wanted to say, as usual, we're gonna get there. Take care of yourselves and take care of each other. And for now, I bid you an adios, and I'll see you in the next video. Bye.